Hey everyone, I'm Harish. I'm Ethan. And we're from FTC Team 12791. This will be our third year competing, and we're excited to present to you our Octocanum drivetrain and the ins and outs of how we created it. So here's the agenda. First, we will be covering an introduction. Then we'll cover why we chose the Octocanum drivetrain out of the multiple drivetrains at FTC, a couple of design considerations, some build challenges along the way, the pros and cons of our iterations, future enhancements, and finally, key takeaways you can take away from this presentation. So let's get right into it. So throughout this presentation, we'll go through a guiding question about is 8 better than 4? So is 8 wheels really better than the standard 4 Octanum wheels in the history of FTCs? So here are the couple of FTC drivetrains that you'll see. One of the most easiest to build is the tank drivetrain, which is very fast and has a good pushing power, but it lacks in maneuverability. You have the X drive, which is holonomic, fast, and agile, but suffers in traction and pushing power. Similarly, you have the H drive, which is also just like the X drive, holonomic because of the H formation. You have four wheels going straight, and you also have one wheel going side to side, but it also lacks in pushing power and traction. You have the Kiwi drive, which is also like the X drive, which has wheels in a triangle formation. This allows for holonomic ability and uses one less motor, but it also lacks in pushing power and traction. And finally, you have the Mecanum drive, which is also holonomic, and the wheels are in a standard condition, just like a tank drive. And the wheel rollers allow the robot to be holonomic and move side to side and move in any vector direction. And then lastly on this list, you have the swerve drive, which is some considered to be superior than all the other drivetrains. It's like a shopping cart drive. So you have the modules on the drivetrain, which can move in any direction, but it suffers in complexity and power drive. And and our drivetrain is the Octocanum drivetrain, which is essentially just the addition of a tank drivetrain and a Mecanum drivetrain, which is a shifting, articulating Octocanum drivetrain, which allows you to have the base wheels, which is either the Mecanum or tank wheels, which can shift down into a different set of wheels, which are shifted. So, what were the benefits for our drivetrain in our season? It allowed for a holonomic ability, so we could still maneuver throughout the poles, but we could still dominate the lanes through the tank drivetrain. And it was defense resistant and it prevented tipping because we could have a mode where all eight wheels were on the field. It had a strong position lock, which allowed us to not be moved when we're scoring. And finally, it allowed for different gear ratios. So we could have one gear ratio for the mechanical wheels, and then we could have a different gear ratio for the traction wheels, which allows for just custom maneuverability. And uh, so, oh, is there? Sorry, the video is over. So it's so here's some design considerations that we had. So we wanted to have a balance between size and weight, torque and speed. This is why we had the multiple ratios. So we had the standard fast ratio for the mechanical wheels to prioritize the speed over traction, pushing power, and torque. We also had a very much lower ratio, approximately two times lower for the traction wheels because we didn't really care about the speed and maneuverability. We only needed to engage it when we didn't want to be tipping, we didn't want to be pushed around, or we wanted to push others around. So this torque and speed balance was extremely important when designing this. We wanted it to be really compact because the second set of wheels would still take up a bunch of space. We wanted to minimize how much space this took up because we wanted to fit in other components, including our turret motors, and also odometry and efficiency. So one problem we had, as I'll show in the other iterations, is that the second wheel would often have less efficiency than the first wheel, and this would be imbalanced between the two wheels because the motors would be situated back. So we wanted to try to maintain the same amount of efficiency in the front and back wheels. And here is our catting iterations. So in our first iteration, we had an 18-inch Octocanum drivetrain, which could strafe obviously, but also have the defense and tip resistance benefits. It was extremely flexible and custom machined. However, some problems with this design is it had the motors extremely high up, which caused for imbalance in the weight. It also had an uneven motor pathing. So one of the motors would have to go through a belt and a gear in order to power the wheel, and one would just go through a belt. And finally, it had a very large footprint, and we didn't want it to be exactly 18 inches, which we didn't really like. So for our second drivetrain, we made it smaller to make it 16 inches. It had the same benefits as before, but one really good benefit about this is that the motors were now much more down. And keeping the motors down would have a better cog, a center of gravity being lower to the ground. And this was extremely good. We had a balanced motor pathing, so the robot was completely symmetrical. And this would allow the weight to be concentrated low and the motors and the wheels receiving the same amount of efficiency, and it was much more compact. We were able to fit odometry much better, and it was overall just a better design. Some cons of still this design was it's still difficult to traverse because the robot is still 16 inches, and we could have made it smaller if we staggered the motors and moved the odometry inwards, but it was still slightly hard to maneuver throughout the field, but our robot's other capabilities just mitigated that. And some of the lessons we learned is to pocket the material to reduce weight, allow maintenance access. We use this through the pocketing. Allow wiring access because of how tight and compact the design is. You want to make sure you have the wiring access for all the components, which are four servos and four motors, and make sure your odometry is accurate. And some of the building challenges that we had and that we wanted to fix was some of these designs that we wish we considered before. One of the largest ones is probably clearance because there was a lot of portions of this robot where, but specifically the drivetrain, where the clearance was less than 1 millimeter in many places, and this would make some things rub against each other if they weren't perfectly accurate. So make sure you check your clearance when you're designing something extremely compact. Catting screws. So there was a lot of portions of the design where we didn't actually cat all the screws, and this would result in two plates that are extremely close to each other hitting and locking onto each other, which forced us to countersink much later than we hoped we would. Speaking about countersinking, make sure you mark all the portions in CAD and in real life about where you're countersinking. Because if you don't do this properly, you might have to build a design, remove it, and then you have to countersink things that you already assembled onto the robot. And finally, calculating screw lengths, because if you don't have the correct screw length, you might have to chop these screws down and make sure you just mark all the screws you have in CAD so you don't waste time ordering more or just creating new screws. And finally, here is the final implementation. You can see exactly what our Octocanum drivetrain was. In the top left, you can see the exact specifications. We were able to host the standard four wheels, as you can see in the four corners. We also have two wheels that not really visible, but in each drive pod, there's two other wheels. They're 2 inches big, and this is the two wheels that shift down into the current robot. We have the servos powering the modules, a nested turret mechanism in the back, and overall the drive pod was 64 millimeters. And probably the most important aspect about the Octocam design was the locking effect that we create on our linkages. So when you lift up an entire 40-pound robot, it requires an absurd amount of energy in order to make this actually succeed. So what we did is we actually had our linkages locked. So our linkages, our two linkage bars actually go exactly at 180 degrees, which essentially creates the force to be mitigated through, as you can see on the graph, we have those two asymptotes. So just explaining upon this mechanism a little more, if you have an elbow and if somebody pushes your wrist along your elbow, without your elbow being completely extended out, it's extremely easy to push it. However, if you completely extend your elbow out and somebody pushes upon your wrist, then your elbow literally locks and it can't really be pushed anymore. This is similarly the same effect as if you're standing. When you're standing, the bottom portion below the knee and the top portion of your thigh locks, which allows standing to be extremely easy and squatting to be extremely hard, which allows for the drivetrain to lock into place when the wheels are completely lifted up or completely deployed down, and reduces completely all power draw that we have when our butterfly wheels are engaged. And you can see that on the graph. So going along, is 8 better than 4? Completely, it can be, but only when used properly.
So we Octam wasn't perfect, and This is our first attempt at it, so there are some things that one can learn from what we did. If we did try this again, or if anyone else tries a similar design, they can learn from our mistakes. So one of them is compactness. So we can reduce the size of the pods and also the motor placements so that we can have more space for our other components, like on our robot we have our lift, but your robot may have other things that need to fit. So you might have to optimize the pods and motors such that it's more compact. In addition, we also have the deployment height. Currently, we lift up our robot quite a bit because we thought that there'd be a lot of tile sag from the heavy weight of a robot, but it turns out that wasn't entirely the case. So we lifted up a bit too much, causing the robot to be a bit tippy. So if we do this again, we might have the butterfly lift up a bit less so that our robot be more stable on the track. In addition, we use odometry for localization, and we use rotationally sprung odometry. However, when you lift up the robot, this causes the odometry pods to move a bit in the translational motion, which would cause drift over time if you're when you integrate the odometry readings. So next time we will try linearly sprung odometry so that the odometry pods won't actually move when you lift up the robot; it just goes up and down. And then lastly, we will reduce the number of servos we use because currently we have one servo for each pod. So that's four servos total. And when you have a lot of different mechanisms, you want to serve the number of servos you use so that you can use them for other parts. So next time we might use two servos, one on each side, so that we only use two servos instead of four, but each of the servos are about twice as strong. And that's just have the same effect, but use less servos so that we don't reach the limit, the servo limit that the hubs are in the rules. And then some key takeaways. Designs may seem complicated at first, but just boil down them to the simple elements of what you want to achieve and what's needed, and then add on complexity from there. Make sure to brainstorm before you start CADing, because if you just start CADing without an idea of what you want, then you can't really get anywhere. So you want to make sure you brainstorm what mechanisms and what sort of things you're having before you actually get into the CADing. And while CAD covers many aspects of the design, there's always other key factors that you might not see in CAD. It's like in our case, we can CAD the screws, and that causes some issues. And there's other things that you may have to keep in mind that can't be exactly seen in CAD, but that as an issue may arise when you start building your robot in real life. So that's one of the things that we have to keep in mind. And keep refining your work. No matter how much you do, you'll never reach perfection, but you can always strive to get as close to that as possible. So just keep on refining your design, seeing wherever you can find a flaw that you can fix or something that you can optimize, and just keep on trying to make the robot as best as it can be, and that'll help you avoid any costly mistakes in the future. And most of all, make sure you don't overwork yourself. I know we're all really passionate about robotics. Sometimes we spend an unholy number of hours on it, but make sure you take frequent breaks and make sure you're not stressing yourself. Otherwise, your mind gets foggy and you can't really think clearly and you can't make critical decisions about designing and building. And also, you might just come to hate robotics or be burnt out, which is not fun. Um, yeah, so that about wraps up our conclusion. Thanks for listening. If you have any questions or want to start things, you can find our socials. We have Discord. You can connect us on Discord. We have a website, an email. Yeah, and we also have an Instagram. So we have a variety of ways to contact us. Any questions?
Yeah, we have two in the chat. I'll go read them out.
Okay.
Uh, okay, so Odoye from Team 21163 asks, are there any weight limitations that the drivetrain must accommodate and how you handle the issues like slippage, skidding, or wheel wear in your drivetrain design?
Yeah, so regarding the weight limit, so we calculated exactly, so we predicted our robot would be like around 40-ish pounds. And the main only limitation that we had was the balance between speed and power draw. So we made sure to keep our wheels within a 17.3 ratio, which allowed for a balance between that speed and that power draw. Regarding lifting the wheels off the ground, this didn't really have any issues about the weight because it would lock, so there would be no power draw when it's fully deployed. And the only time we encounter any force is when we're actually lifting up, currently actively lifting up the drivetrain. However, this was accounted for. We're using four 25 kg servos, which can take up an absurd amount of load because of how small our lever arm is. So that's how we accounted for it.
We calculated it such that the servos can approximately lift about 80 pounds, so that was like twice what our robot weighs, just to make sure that we don't encounter any trouble when lifting our robot up.
And regarding the wheel slippage, so that was the one of the main aspects of why we had an Octocanum drivetrain is because the mecanum will slip, and that's how it's able to straight. However, we didn't really want that when we're like going regarding defense, or if somebody's pushing us, or if we don't want to tip. And that's why we have these Gray Grippy Tread custom 2-inch grippy wheels for our tank drivetrain when we shift into it, which we didn't really have any issues about wheel skippage because of how small the wheel is, how much weight is being applied onto it, and then finally the material it is.
Right. Yeah, last question is, do you plan on using this drivetrain for future seasons?
I'd say yes. If we don't find a better one, then yeah, we'd probably use this.
Right.
Cool.
How often do you actually switch it to tank drive mode in this match?
Yeah, so we used to switch it decently less in like regionals in our four competitions, but in worlds, I think we'd switch at least 4 times a match. Especially when we were controlling lanes.
Yeah, and in like regional and like some lower levels of competition, we didn't need or want to play defense as much. But in Worlds, it was quite a bit more competitive. So we just went full ham. New start driver was able to push the robots and dominate the lanes with the tank drive. And then once he puts them out of the way, you can switch to Magnum and then start scoring cones.
All right, cool. Thank you, Iterative Intentions.